All right, y'all. So let's talk about electron configuration. We'll talk about the periodic table and we've talked about these sublevels with quantum numbers, these 4 different quantum numbers. We'll talk about how that relates to electrons in elements on the periodic table. So real quick, the electron configuration talks about where the electrons are in the atom, right? It describes, again, those quantum numbers. It kind of coordinates for where the electrons are. When we write electron configurations, our ground state is going to be the most stable configuration. That's typically where the atoms want to be. And one thing that I want you to know when we write out these electron configurations is that we fill orbitals. So now we've talked about orbitals. We know what these orbitals are. We fill them in order of increasing energy. Okay, remember, an orbital can only have a maximum of 2 electrons, whether it's one of the s orbitals or the s orbital, or one of the p's or the d's. It can only have a maximum of 2. And this box right here is a box representing an orbital. The maximum amount of electrons that can go into each box is going to be 2. Okay. We represent arrows with these we represent electrons with these half arrows. So this is 1 electron here. This is a second electron. And remember, m sub s can either be plus or minus half. Each of these spins, each of these kind of opposite represent 1. So you can set the up as a plus half, the down as a negative half, or vice versa. It doesn't matter. 2 electrons in the orbital, one's going to be a plus half, one's going to have a negative half spin. Okay, there are a few principles that drive electron configurations. One of those is the Aufbau principle that says when we fill our orbitals, when we kind of add electrons, you have to fill from the lowest energy level first. 1, this is the ground state, 1s is the lowest, followed by 2s, and then the p's, and then 3s, and so on and so forth. I'll show you how to actually figure out how these things fill, but Aufbau principle says, hey, we're going to fill from the lowest energy level first. The second is the Pauli's exclusion principle. Remember, it says, hey, each orbital can have a maximum of 2 electrons, and no 2 electrons will have the same 4 quantum numbers. So the principal quantum number can be the same, so n, L can be the same, m sub L can be the same, but m sub S will have to be different. Okay. And then finally, Hund's rule. Hund's rule says, essentially, we're not going to pair up electrons until in an orbital we filled every single spot in that orbital. So for example, the p orbital has 3 things, right? And if I were putting electrons in, I couldn't do this. I would have to first fill every orbital, right? If we have an empty orbital, and I have the electrons to put in there, I have to do that. If I don't have electrons, it is what it is. But if I have electrons, I have to first put one at a time, okay, to fill the orbitals. Okay, so those are the 3 rules that govern what we do in terms of electron configurations. So for example, remember, so let's go back to our periodic table, go back to what we talked about earlier on in the semester. If you look on the periodic table, you see the number of protons, and for neutral atoms, the number of protons equals the number of electrons. And so I can figure out the total number of electrons by looking on the periodic table. So for example, lithium has 3 electrons. Here's how I would fill that out. Okay, beryllium 4, here's the fill. Nitrogen has 7. I would, again, first fill that, and then fill that, and then put 1 of each in there. Okay. Neon has 10. Here's what that looks like, and so on. And the electron configuration literally is just saying, hey, this is the 1s orbital, and I have 2 electrons there. That's what that 2 means. 1 in the 2s. Here I have 2 in both, and that's what those numbers mean. 2, 2, 1. Again, those numbers, and so on. Okay, so let's talk about what we see when we do these electron configurations, when we write them out. Kind of talked about that on the previous slide. But when you look at the electron configuration, it's going to look something similar to this. And the big number, that 4, the 1, the 2, whatever that is, tells you what the energy level is. That's n. Okay, so that big number is your n. It's then going to tell you the type of orbital. This is going to be your L. Remember, S, P, D, F, L would be 0, 1, 2, and 3. Sorry, my pen went off. And now we're frozen. And then the 5 would denote whatever the number of electrons are. Hopefully I come back on soon. But yeah, so it would denote the type of electron. So the 5 would be how many electrons that I have. Okay, I'm back. Sorry, guys. But essentially, so 4 tells you what the energy level is. P would be your L, so angular quantum number, and remember S, P, D, F, 0, 1, 2, 3. And then 5, or the subscript, would be how many total electrons you have in those orbitals, and we can figure out how many electrons we have in those orbitals based on how many orbitals we have, and each orbital can have a maximum of 2 electrons. Okay. So for example, for carbon, here's the electron configuration. It has 2 things in the s orbital, in the 1s orbital, 2 in the 2s, and then 2 in the 2p orbital for a total of 6 electrons for carbon. Okay. So there are a couple of ways to think about how to write your electron configuration. Again, if you've done this before, you probably have seen one or the other. I don't care which way you use. But when you look on the periodic table, there are 4 blocks. This part of the periodic table is your S block. The other side, so that the S block would be the 2 groups 1 and 2. And then on this side, it'd be groups 3A, 4A, 5A, 6A, 7A, 8A. That's your P block. And then your transition elements would be the D block and then F block. Okay. And so if you think about it this way, this is the route I'm going to use. This is how I'm going to talk you through filling the electron filling. This would be your period 1, that's n equals 1, period 2, n equals 2, period 3, n equals 3, n equals 4 for your S and D and P, but note for your D, that's at n equals 3. So the D block is always going to be 1 less in terms of the energy level than the S and the P. F block is going to be 2 less than your S and your P, and then 1 less than your D. Okay, so you can fill, I highly recommend filling, looking at the periodic table and doing that way. Another way you could do that is just write 1s, 2s, 2p, 3s, 3p, 3d, like, and so on. And the way it fills is it would fill first 1, and then 2, and then 3. So if I were writing this, I would write it as 1s first, and then 2s, and then 2p and 3s. And then do that 3p and 4s and so on. Okay, so you could do it this way if you've seen it this way. If you've never seen any of this, I recommend doing it this way. Okay. There are 2 ways that I will usually write our electron configuration. Again, this is a different, same idea, but a different way to look at this kind of the fill pattern. I can either write by fill order, so I fill 1s first, and then 2s, and then 2p, 3s, and so on. Or I can write it in terms of energy level. So I put all the 1s together, all the 2s together, all the 3s together, all the 4s, and so on. Okay. Doesn't matter which way you look at it. I usually do fill level or fill order. But yeah, either way would be right. Note, we had talked about this earlier, but the s orbital can have a maximum of 2 p electrons. P can have a maximum of 6, and that's why you would have 6 total. D can have a maximum of 10. And F can have a maximum of 14 electrons. Okay, you do need to know this. All right, so I can write the electron configuration by just writing the 1s, 2, and so on, and that's very tedious. It's a lot of stuff. Or I can write it in a way that is called the condensed electron configuration. And so I just look at, all right, what's my closest noble gas to where I'm going? Put that noble gas down and then just write the valence electrons, okay? Valence electrons are the electrons on the outermost shell of whatever atom or element that you're looking at. We'll talk about bonding in the next unit, but the valence electrons are the reason that bonds occur, ionic or covalent, and then we call those inner electrons, so anything that's not on the outer shell, we call those core electrons, okay? I can either write my electron configuration saying, hey, 1s, 2s, 2p, and so on, or just write it in the condensed version. I'll talk about what that looks like in a little bit. So here's what that condensed electron configuration would look like. Okay, so if you look on the periodic table, real quick, grab your periodic table, pull it up, look at beryllium, you'll see that the first noble gas you hit on your way to beryllium is helium, and helium has a 1s2 electron configuration, but instead of writing that out, I just put helium in parentheses saying, hey, the electron configuration for that noble gas, and then the valence electrons for that. So for beryllium, it has 2 valence electrons, magnesium also 2. All these have 2 valence electrons, and spoiler alert, they're all in group 2. Okay, so everything in group 2 will have two valence electrons. Group 3, on the other hand, again, these are my outer shell, outer electrons, N equals the same thing. And they all have 3 valence electrons. 2 plus 1 is 3. Okay, so different energy levels, but the total number of electrons on the outside is all the same. Okay. There are irregularities to electron configurations that you are responsible for, and that's because of stability. So when I can half fill either my s or my d orbital, it's preferred than kind of filling in a way that offsets stuff. So I would rather have, I'll show you in a bit. So for example, chromium is right here. And the way you would fill that up would be 4s2 and then 3d4, right? We fill up in terms of like how we hit energy level and things like that. But it's actually better to have a half-filled S and a half-filled D as opposed to, so if I were to draw this out, this would be my d orbital. And the typical way that you would expect, it would be 1, 2, 3, 4 for D, and then 2 for the S. But this is actually a lot higher in energy because the 3D actually is higher in energy than 4S, even though the number is a little bit lower. But because there are a ton of electrons there, it's higher in energy. So the preferred way is actually to have everything half filled and nothing empty. So these are irregularities that you are responsible for, and these are the irregularities, right? So chromium, copper, molybdenum, Ru, and then PD. Okay, these are the ones that I would typically expect. This is what I would usually test on. These ones we don't see too much of. Okay, here's a way that I would write this out. So taking my quantum numbers and then the electron configuration, here's how I would write this out. Okay, so helium 1s2, N is 1, right? There are 2 electrons here, and so I can tell you where those 2 electrons are, or the coordinates for the 2 electrons. Both are in N equals 1, right? S is L, which is 0. M sub L has to be 0. But my M sub S for one of those is going to be plus 1/2. N, L, M, all the same. But for that second electron, it's going to be the opposite of the first one. Because again, Pauli's exclusion principle says, hey, I can't have 2 electrons that have the exact same 4 quantum numbers. Okay. And that's it for that.